The content in this presentation is covered on pages 179 through 191 of your textbook, and it's meant to help you achieve learning objective number 30, which is to describe atmospheric conditions that produce sleet, freezing rain, rain, and hail. Be sure to skim these pages before watching the video and to read more carefully before attempting the online quizzes. Atmospheric conditions vary greatly, and that causes several different types of precipitation to form. Sleet, freezing rain, and hail often produce hazardous conditions on the ground. Rain and snow are more common and familiar weather, and they occasionally inflict considerable damage. When the air is full of moisture and the temperature drops, fog or mist may occur. Fog or mist is simply a cloud at ground level, and it consists of countless tiny droplets of water suspended in the air. Light passing through the fog scatters in every direction, making it translucent, so light will pass through it. Looks kind of like a tracing paper. In thick fog, visibility can be reduced to less than a few yards. Precipitation containing the very smallest droplets able to reach the ground is called mist. Mist can be so fine that the tiny droplets appear to float, and their impact is almost imperceptible. Mist closely resembles fog. Meteorologists use the word fog when the visibility is less than a half a mile, and mist when the visibility is greater than a half a mile. Droplets large enough to be felt on the face when the air is moving about a meter per second, that's mist, and it's usually associated with stratus clouds. Drizzle is very light rain that's produced by low clouds. So drizzle can be found anywhere in the world. However, if the temperature is below 32 degrees Fahrenheit, the drizzle will become freezing drizzle, which has a more disastrous effect than regular drizzle. Fine uniform droplets of water with diameters less than half of a millimeter are called drizzle. Drizzle and small raindrops generally are produced in stratus or nimbostratus clouds, and that precipitation is usually continuous for several hours or I guess sometimes as long as a day or so. Drizzle is really small uniform droplets that fall from stratus clouds. And let's see, rain. The term rain is restricted just to those drops that fall from a cloud and have a diameter of at least 0.5 millimeters. As rain enters the unsaturated air below it, it begins to evaporate. So you may be familiar with that sense of that humid air that surrounds you during a rainstorm. That's because there's a lot of evaporation happening. Most rain originates from either nimbostratus clouds, like you see here, and it tends to be low intensity, light rain in these cases that'll last for a day or two. Or you can also have rain falling from towering cumulonimbus clouds. And in those cases, it tends to be heavier rain and much shorter in duration. So in some cases, cumulonimbus clouds produce unusually heavy rainfalls known as cloud bursts, and those can cause intense flooding downstream. I think that the Big Thompson River reference from previous lecture was an example of a really unusually large cloud burst. As I said before, though, rain begins to evaporate as it enters the unsaturated air underneath the clouds. Depending on the humidity of the air and the size of the drops, rain may completely evaporate before it reaches the ground. And that phenomenon produces virga, which appears as streaks of precipitation falling from a cloud that extend towards Earth's surface but never quite reach it. Similar to virga, ice crystals may sublimate when they enter the dry air below. So this is how you get a fall streak when you're talking about cirrus clouds and ice crystals. Winter precipitation now, small spherical lumpy ice particles that form when raindrops freeze while falling through the layer of sub-freezing air. That's sleet. Sleet is a wintertime phenomenon, and it consists of small, clear to translucent, spherical to lumpy ice particles. And you can see, based on the intensity and duration, you can cover the ground with sleet like a blanket of snow. And because those particles are small, they don't usually generate much damage, but they do make travel hazardous. Here I can see a bunch of precipitation that fell on the street here. A car has clearly driven through, but I can see individual particles of ice. There's one, and there's one. I'm not drawing anything, am I? But here's one, and here's one. So individual pieces of sleet can be seen in that layer of precipitation. Freezing rain, on the other hand, falls as supercooled raindrops that freeze on contact with some object that's below freezing. So roads, power lines, other structures, your car, sidewalks. Freezing rain forms a thick coating of ice that has just enough weight to seriously damage trees and power lines. Both sleet and freezing rain occur in the winter, most often along a warm front where a mass of relatively warm air is being forced over a layer of sub-freezing air near the ground. And as you'll see in a minute, both sleet and freezing rain begin as snow, which melts to form raindrops as it falls through the layer of warm air below. Rime is a deposit of ice crystals formed by the freezing of supercooled fog or cloud droplets on objects whose surface temperature is below freezing. So when rime forms on vertical objects like rock outcrops or trees, it covers them with its characteristic ice feathers that point into the wind. So they point towards the direction the wind is coming from. These delicate frost-like accumulations form as supercooled cloud or fog droplets encounter objects and freeze on contact. Snow is a form of winter precipitation in the form of ice crystals or aggregates of ice crystals. The size, shape, and concentration of snowflakes depend to a great extent on the temperature profile of the atmosphere. So remember that at very low temperatures, the moisture content of air is very low. The result is generation of a very light and fluffy snow made up of individual six-sided ice crystals, hexagonal crystals. This is the powder that skiers covet. By contrast, at temperatures warmer than about -5 degrees C, or 23 degrees Fahrenheit, the ice crystals may join together into larger clumps consisting of tangled aggregates of crystals. So snowfalls consisting of that composite snowflake are generally heavy and have high moisture content, and that makes them ideal for making snowballs. Snow can reach Earth's surface when the temperature of a thin layer of air near the ground is above freezing. And in that situation, the snow doesn't have to move, doesn't have enough time to melt before reaching the ground. That kind of snow is usually pretty darn wet. Under certain atmospheric conditions, falling snow crystals grow as they intercept tiny supercooled cloud droplets that freeze on them. The resulting snowflakes are described as being rimed. So if riming continues and makes the shape of original six-sided snow crystals no longer identifiable, the soft ice pellet is called graupel. Usually they're oblong in shape and fragile enough that it will fall apart when they're touched, but graupel is also known as soft hail or snow pellets. Hard or rounded pellets of ice form in cumulonimbus clouds, and they are called hail. Hail is precipitation in the form of a hard rounded pellet or some kind of lumpy shape of ice. Diameter is usually 5 millimeters or more. Hail is produced in the middle to upper reaches of tall cumulonimbus clouds, where updrafts can sometimes be greater than 100 miles an hour, and where the air temperature is well below freezing. So they begin as small ice pellets or graupel that coexist with the supercooled droplets. And the ice pellets grow by collecting supercooled water droplets and sometimes other small pieces of hail. Cumulonimbus clouds that produce hail have a complex system of updrafts and downdrafts. A region of intense updrafts suspends rain and hail aloft, producing a rain-free region surrounded by an area of downdrafts and heavy precipitation. So the largest hailstones are generated around the core of the most intense zone of updrafts, where they rise slowly enough to collect appreciable amounts of supercooled water. And the process continues until the hailstone simply grows too heavy to be supported by the updraft, or it encounters a downdraft and falls to the surface. There are actually two methods through which hailstones can grow: wet growth and dry growth. And they can make the hail appear sort of layered looking or like milky ice. Clear ice is usually produced by wet growth in lower and warmer regions of the clouds. And as droplets freeze to those hailstones, the air bubbles in the water are escaping, producing a relatively bubble-free clear ice. If they're forming in the high parts of the clouds, where the temperatures are below freezing, supercooled droplets immediately freeze when they collide with the growing hailstone, and the air bubbles are frozen in place. So that leaves them looking sort of milky. And in this picture, I can see some that look milky and some that look clear. Here's a milky looking one. So this is wet from high up in the cloud. And this is a clearer looking one, right? Most hailstones, like I said, are between pea-sized and golf ball size, although there have been some as big as softballs, and in Wyoming once I remember seeing a picture of somebody with one that was more like cantaloupe bowling ball sized hail. The record was actually in the United States, in South Dakota. The hailstone was about 8 inches in diameter. So that's a big bowling ball. Let's see. Larger hailstones have been reported in other parts of the world, but not confirmed. And so if you look at shows like Storm Chasers, you might see Reed running around and trying to catch hailstones. The big industry, especially in this part of the world, is making composites for aircraft that can withstand collisions with hail objects and with hail. And so people go about collecting hail to study that sort of physics. So this is a graupel. This is the soft hail that forms as rime collects on the snow crystals. So that's the soft ice. Okay, most precipitation that forms in the wintertime starts out as snow because the top layer of the storm is usually cold enough to make snowflakes. And snowflakes are just collections of ice crystals that cling to each other as they fall toward the ground. When we get precipitation that ends up as rain when it hits the ground, the snowflakes fall from the cloud into a layer of air that is probably below freezing, 10 degrees below freezing in this diagram. The freezing level, or you could think of it as a melting level in this case, is somewhere high above the ground. And that means there's a thick layer of relatively warm air that continues all the way to the ground. Because the snowflakes are relatively small, they fall slowly enough through the warm layer to allow them to completely melt and even warm up a little before they hit the ground. So if we're looking at a temperature data from an atmospheric sounding, the temperature profile would look like a straight line with the air being warmest near the surface. In the case of freezing rain, the snowflakes descend into a warmer layer of air and still have enough time to melt completely. But because there's a thin layer of freezing air just above the surface, they don't have enough time to completely refreeze before they reach the ground. They do, however, refreeze when they hit the ground. Notice that the freezing level isn't any closer to the ground in this case. But the layer of cool air near the surface makes the warm layer thinner. Even though the settling velocity of the flakes is still low enough to melt them in the warm layer, they will then pass through a second freezing level located high enough above the ground to cause them to supercool before they strike the surface. The droplets then refreeze upon contact with a temperature at or slightly below freezing, creating a glaze of ice that's measurable in some cases. Even light accumulations can cause dangerous travel, while heavier amounts cause significant damage to trees and power lines. So a significant accumulation of freezing rain lasting several hours or more is an ice storm. Notice that the temperature profile in this case looks like an archer's bow, almost symmetrical, with the inflection point, the bending point, about halfway through the curve. For sleet, the bend in the temperature profile occurs much higher in the sky because the layer of cold air near the surface is much thicker. So sleet occurs when snowflakes only partially melt as they fall through that thin layer of warm air. In this case, the cold surface air layer is thick enough, or the freezing level is high enough, that the droplets do have time to refreeze before hitting the ground. The surface temperature has to be well below freezing for sleet to form. Notice that the temperature here is minus 10 degrees compared to minus 5 degrees in the case of freezing rain. The drops that became partially melted had a slushy texture as they fell through the warm layer, but freeze hard enough in the surface layer that they actually bounce on impact. Depending on the intensity and duration, sleet can accumulate on the ground much like snow. So compared with the slick layer of glaze in the previous slide, you can see the individual particles usually in the case of accumulated sleet. Snow occurs simply when there isn't a layer of warm air present between the clouds and the ground surface. And in this case, the snowflakes fall all the way to the ground without melting because the temperature remains at or below 32 degrees F from the cloud base to the ground. So the temperature profile here is completely on the cold side of the graph from tip to tip. We tend in the Puget Sound region to get this situation only when the Fraser River Valley is conducting really cold air from the northeast to the southwest. And then the whole Puget lowland fills with that cold Canadian air. And that's when we get snow like we've gotten this winter so far. So use the content provided on the Canvas site as well as outside sources to verify that you can formulate answers to these questions. If you're comfortable answering them, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.